All right, are we working? I don't know what we're doing. Let's look at Ladybug again. Sure. Okay, we're gonna see how this works. I have no idea if any of this worked, but let's talk about what we're doing today so that I know everybody's in good shape if we don't have class. All right, so the first handout that you have is the border problem. And if you read the textbook for the border problem, you will see, I want to look at that some more. Let's go back here. Let's go over here. Okay. Can I get into the meeting? How do I get in the meeting? Well, I guess I'm in the meeting. Will it let me go to the interwebs? All right, let's go back to the video. Okay, so we're going to start again and I'll edit this. So the border problem we've done before, and it's where I show you a square, and it's a 10 by 10 square, and I want you to tell me how many squares make up the border. And we treat this one like a number talk so that I get answers from you that are different than just 36, right? How did you get to that 36? I don't want anybody to count them. And so the first problem that we have, or the first handout, has to do with that. So I look at, this is straight from the book, so if you're worried where this information comes from, it's straight from the book. And it's looking at how this particular student came up with his solution to how many squares are in the border. So he did 10 times 10 times 4 minus 4. And that's correct, right? It gives you 36. But then he described how he got there in words. So we've got a 10 by 10 square, and he had 10 squares along each of the 4 sides, which gave him 40. But then he had to take away 4 so that, because those were all counted twice along the side. So that's how he came up with this particular formula, 10 times 4 minus 4. So that's the first part. And you're going to think about this, see if you like it, see if it makes sense. And then after that, we're going to continue with the border problem, and you're going to look at other students' solutions. So Valerie calculated her solution as being 10 plus 10 plus 8 plus 8. And I have my pictures of what I did. So 10, whoopsie. And it would be, this is what I'm looking for. So I'm looking for you to go, okay, well, here's Valerie's. She did 10 by 10 plus 8 plus 8. So that was what her picture looks like. And then the next picture is 4 times 9. Well, I've got 9, 9, 9, 9. And how did Linda get hers? Well, she had a 10 by 10 square, and then she found the area of that, and then subtracted the area of the 8 by 8. So you're going to do something like that. And graph paper is great, but you don't have to use it. So then once you've looked at all of these and drawn them and made sense of them for yourself, you're going to go into a 6 by 6 square. So instead of a 10 by 10, what's a 6 by 6 going to look like? How many unit squares along the border are you going to have? And you're going to take 2 of the techniques that are above here, and you're going to adapt them for a 6 by 6 square. And you want to use your colors, draw your pictures, all those good things. Okay, so where'd the other page go? Here it is. So then you're going to think about it in terms of a 25 by 25 square. Same idea. And so once you've done all of these, I would suggest you look back and find a pattern, find a rule that applies for the number of tiles, the number in the border, of tiles in the border, and the dimensions of the square. The border and tiles and dimensions of the square. So come up with a generic nth term if you were trying to figure out a square of n by n. And once you have that, the rest of it's easy because then you're working backwards from here. So now they're saying, here I have 64 red squares. How can I use those squares to make a border? Can I make a border with just 64? And to come up with a way you can do that. And then the same for 30 and 256. And last but not least, you are going to show what your n by n square would look like. And then if you had some number of k red squares, how would you come up with a quick test to see that they worked? All right, that's the border problem. After the border problem, we've got the mobile problems. And I'm just going to show you one because I think these are so cool. All right, this guy, I have one of his books, but they're out of print, and they showed up in my new Mindset math book, and I was so excited. But it's pretty easy to use. Here we go. So you've got some weight up here. So this is 16. So this is telling me that this is perfectly balanced at 16 pounds, which means that this half is balanced with this half. And in order for them to be balanced, because this is a mobile, however you say them, mobile, each side has to weigh 8. So hopefully that makes sense. So they have to have the same. And then if you come over here, well, these two combined weigh 8. So that means that each side of this has to weigh 4. And then on this one, these combined add up to 4. And this one, so this has to add up to 4, this has to add up to 4, 4, and 4. All right, so we're ready for this? I think we can do this now, which also means that these have to be 2 and 2. So over here, it's probably easier. We can see that this is 1, 4, sorry. It's hard to talk on camera as it is in person. Good grief. So we've got 4, and then so this one has to weigh 4, which means this one has to weigh 4, and that jives, right? Then this one, these have to be 2 because the shapes are the same. They have to weigh the same, and that jives because 2 plus 2 is 4. And over here means this one is 2 also, right? That makes sense. And this one, so there's 2 of these. They should each be 1. And that's how these work. They're super cool. So we have quite a few of them. The ones you have to watch out for are, there's one that has 3. Where is it? Oh, not in this one. All right. 16, 60, 24, 48, and 80. All right. So you've got those to do. Next, we're going to talk about what the equal symbol means in math. And these are all straight out of the book. So I just want you to know if you're not understanding what's going on, feel free to just go to the book. All right, so we're looking at the equal symbol, and you want to look at these first ones to see which ones are always true, sometimes true, or never true. Like if you look at A, 5 plus 3 is always 8. There's no question about that. And n plus 3 equals m, well, just depends on what you put in here for n and m. So that's sometimes true. And 2/3 plus 1/2 is never 3/5. So that's what you're doing on these. Here's another problem you're going to solve. Come up with how much money Akira had. And here's Kim's solution. And I want your opinion of what you think about it. And then over here we have some more balance puzzles. Yay! And they are from the book, so you can pull them off of there if you're confused. And these are set up a little differently, so they have some rules. They tell you what they are. Total weight is 36 grams. All shapes weigh less than 10. All the weights are whole numbers. And one circle weighs more than one square. So you'll just build those just like the other mobile problems. So we've got a couple of those. And because there's always more. Then we've got some balance problems, which you'll use. This is a lot of how they teach equation solving now. So they've given us the rules here, and the colors aren't great, but again, this is in your book, so you can see what we've got. And you're just trying to figure out, okay, well, what's happening here? So if two triangles are the same as a square and two circles, well, what do you know about the circles? Well, I think it's since we've got two triangles over here, and a triangle and two circles make this perfectly balanced, well then two circles is the same as one triangle. Does that make sense? So you're working your way through those. There's a bunch of them. Then you get to play with it a little bit, make your own. And last but not least, we have a strange little algebraic thinking warm-up. Excuse me, as always, my phone is blowing up. This is fun. So this is a cat machine. You've got this wacky veterinarian. They have a cat machine, a dog machine, and a mouse machine. In the cat machine, you place a cat in the bin, and you press the button, and out comes two dogs and a mouse. Then the machine, so that's how that one works. So one cat equals two dogs and a mouse. For the dog machine, well, one dog equals one cat and one mouse. And the mouse machine, you've got one mouse goes in, and a cat and three dogs come out. So this is kind of a function machine, right? We're taking a cat, putting it in the function, chugga, chugga, chugga. We have two dogs and a mouse. That's how it works. So these are some scenarios, and this vet, not only is he wacky, he has some demands. So he's going to give you two cats, and he wants you to convert them into exactly three dogs. And that's all he wants is three dogs. No extra cats, no extra dogs, no mice, nothing. Just three dogs. Can you do this? So you're going to play with these and see if you can make that happen. The machine also goes in reverse. So if you have a cat and three dogs, if you put them back in the mouse machine, you'll get a mouse. So they work in reverse as well. All right. So I think that's all I've got. So hopefully that explains things. If not, we'll talk more. And I'm going to try and see if I can make this Zoom work for class tonight. Should be entertaining. If we have it. It's still snowing here, but no one's called it. If you have any questions, let me know. And I will see you soon. Bye.